I apologize for the interruption. So we continue with our examples. So let's use the Dedekind product theorem to compute this degree. And you might expect again that this is going to be a lengthy calculation, but in fact, in this case, it's a lot easier than the previous case. So you already know how to start. We start the same way as last time. So we write our base field at the bottom, and the field whose degree we're interested in, we write at the top. Okay, and now you can sort of choose whichever field you're going to put in between. I'm going to write both of them, but I'm going to use one of these paths to get to the top, right, to be able to actually find this degree. And in fact, one of them is easier than the other in this case, and you will see in a moment why. Okay, so the easier path is this one. So I first notice that the degree here is 2. Okay, and you already know why, because the minimal polynomial of radical 7 over q is x squared minus 7. This polynomial is irreducible, and it has radical 7 as a root, coefficients in q, and is monic. So that's the minimal polynomial. Okay, and then I look here, and I argue the same way I started last time. So I would say, oh look, this field here I can write, you remember the order doesn't matter, so I can write as this, and then adjoin radical minus 3, right? This is like the f. So this field then is like f of alpha. So if I could only find the minimal polynomial of this over that, I would be done. So I first note that, just like last time, note that radical minus 3 is a root of the polynomial x squared plus 3, which has coefficients in q. I'm going to leave a little space here. It has coefficients in q, but therefore it also has coefficients in this f, because any rational number is contained in here. So it has coefficients in here. Think about what's the conclusion from that about this degree here. Does it mean that the degree is 2? No, because I don't know that that's the minimal polynomial, right? But because I found a quadratic polynomial which has the right coefficients and is monic and has a radical minus 3 as a root, that means the degree is less than or equal to 2. So if I call this degree d here, so d is less than or equal to 2. Yeah, the minimal polynomial is either this, so it's 2, or it's of degree less than that, so that would be 1. What are the two options then for d? 1 or 2? If d is 1, then remember that means that these two fields are equal. What does that mean if they're equal? In particular, that means that, well, radical minus 3 definitely belongs to this field, to the right-hand side, so it must also belong to the left-hand side. Hence, radical minus 3 belongs to q adjoint radical 7. Okay, and I could now go like I did last time. I would say, well, so radical minus 3 is equal to a0 plus a1 radical 7, where a0 and a1 are rationals. Try to square both sides and get a contradiction. But in this case, there's actually an easier way, because everything in this field can be written as a0 rational plus a1, which is rational, times radical 7. So everything, I know that rational plus rational times radical 7 is always a real number. So everything here is a real number. So this field is contained inside the field of real numbers. Do you see a contradiction right there? Yeah, this is not real. But radical minus 3 is not real. Contradiction. So this degree d is 2. So once I know that the degree is 2 here, the degree of the top over the bottom is 4. And we answered this question already. It was much quicker than last time because one of these numbers that I was adjoining was not real and the other one was real. You see, if you chose this path here, if you first adjoined the square root of -3 and then adjoined radical 7, you wouldn't be able to use this sort of argument. Because you would say here that you would have q adjoined radical -3 equal to that field, and you would say also therefore that means that radical 7 belongs to q adjoined radical -3. But radical 7, well, it's a real number, so it's a complex number. There's no contradiction it lying in q adjoined radical -3. Okay, there is a contradiction from radical -3 lying in this field because this field is completely contained inside the real numbers. Let's go one step further in this example and actually let's find the bases. So if you recall from one of the previous videos, a basis of f adjoint alpha can be taken to be 1 alpha squared all the way to alpha to d minus 1, where d is the degree of the minimal polynomial of alpha over f. Okay, so let's look at this. So a basis of q adjoint radical 7 as a vector space over q would be, well, okay, let's start 1, then alpha, so radical 7, and I'm supposed to go to the power 1 less than the degree of the minimal polynomial, but the degree of the minimal polynomial is 2, so I stop there. Now let's do this. Basis of q adjoint radical -3 radical 7 as a vector space over q adjoint radical 7. All right. Again, what am I doing here? I'm adjoining radical -3, so I go 1 radical -3, and how far should I go? Well, look, I know now that this is the minimal polynomial of radical -3 over q adjoint radical 7. I know that, right? Because it's of degree 2, and I found that the degree is actually 2. So, because it's 2, I stop there as well. So now by the Dedekind product theorem, Dedekind product theorem not only gives you that the degrees multiply, it also tells you how to get the basis. If you recall, it just tells you, you take every element here in this basis and every element in that basis and just multiply them together, look at all the possible combinations. So that tells me that the basis of q adjoint radical -3 comma radical 7 as a vector space over q, not over q radical 7 but over q, is, okay, so I take 1 radical 7, right, that's this times that, this times that, now this times that, so that's radical -3, and finally I do this times that, that's radical -21. Okay, let's do another example. So example 3, find the degree of q adjoint radical 3 cube root of 2 over q. Okay, so now it's not only just two radicals, two square roots, but one of them is a cube root, and none of these numbers is not real. So let's see how difficult that's going to be. In fact, it's not going to be difficult again for a different reason this time. So we start off the same way, right? Q at the bottom and q radical 3 cube root of 2 at the top. And I'm going to choose this path by first adjoining the higher degree root rather than the lower degree. Sometimes that's easier. Again, you could have chosen the other path as well, and we're going to actually fill in the diagram here too. Okay, that's of course what I want to know. All right, I pause for a second, or you should pause for a second, and tell me what is the degree here. Okay, now that you unpaused it, I'm sure you have found that the degree is 3, because the minimal polynomial of cube root of 2 over q is of degree 3. Right? That's the thing. That's the 3 here. So I need to now find this. How do I do this? Again, the same way. You can again pause the video here and try to argue what's this number here between those two fields. And let me now show you how to get it. So this is q adjoined cube root of 2 radical 3, right? That's my f. So I just want to know what is the minimal polynomial of radical 3 over the field q adjoined cube root of 2. I definitely know, so note, let's call this d. Note, radical 3 is a root of x squared minus 3. And this polynomial, again, it looks like it has coefficients in q, but if it has coefficients in q, then it also has coefficients in any field that contains q. So it has also coefficients in q cube root of 2. So d is at most 2. What if it, what can it be then? 1 or 2? If d is 1, then I get that, oh, you know what? We don't even have to argue, we don't even have to worry what happens when d is 1. Because, in fact, let's use the other path here as well. So what's the degree here? The degree here is 2. Because the minimal polynomial of square root of 3 over q is x squared minus 3, right? So the degree here is 2. And I don't know this guy here. But, and let's call this question mark, right? The one that I want to know about, x. So the Dedekind product theorem gives me some very interesting information. It tells me that x is equal to, well, I can go up this way, so it's 3d, or I can go up this way, so it's 2e. Okay, look at this. This is actually quite useful. This means that 2 divides 3d. But 2 is a prime, so it either divides 3 or it divides d, so it must divide d. So I claim we already have an answer. If you wish, you can pause the video here and think about this answer. Okay, let me tell you why we already have an answer. Because we have that d is less than or equal to 2, and on the other hand, I know that d is divisible by 2. So that means that d must be 2. Clever, huh? So without doing any messy calculations, I know that d is 2. So I get that x is 3 times 2, so 6. Note also that as a side effect, I know that e must be 3. That was not part of the question, but I get it. I get that e must be 3, again, from this equation. So x, this degree then, is 6. So I said that in this case we're able to again get a much simpler way of getting the degree than in the first example, and that I used something else than one of the elements being not real. Indeed, what I used here was that these two degrees were relatively prime to each other, and so you see I was able to play it off via divisibility. What about bases? Let's find quickly the bases. So basis of q adjoin cube root of 2 as a vector space over q. Well, again, I'm adjoining cube root of 2, so according to that theorem, I know I just go like this. How far should I go? Well, the degree of the minimal polynomial of cube root of 2 over q is 3, so I go to 1 power less, so I go to square. Then the basis of q adjoin cube root of 2 radical 3 as a vector space over q adjoin cube root of 2, well, that's going to be 1 radical 3, and I stop here, right? Because I know that this polynomial must therefore also be the minimal polynomial of radical 3 over q adjoin cube root of 2, because I found that the degree is 2. So by the Dedekind product theorem, I get that the basis of q adjoin cube root of 2 radical 3 as a vector space over q is, well, all the possible combinations here, all the possible products. So each of these elements multiplied by 1, and then each of these elements multiplied by radical 3. Six elements in the basis. The dimension of q adjoin cube root of 2 comma radical 3 is 6 over q. So it's all consistent.